Hello students, in today's session we'll discuss about the stepper motor and its interfacing with the 8051 microcontroller. What is stepper motor? Stepper motor which rotates in the step. Mainly it converts the electrical pulses into the mechanical movement. They are mainly used for position control like in the disk drives, dot matrix printers or robotics. In the disk drives, mainly the motors are used to position the head on required sector and track. In case of a disk, there are number of tracks and sectors and the file that is to be accessed. For that, the head has to be positioned properly. Similarly, in the dot matrix printer, for positioning the head so that the printer will start printing from left to right, or say moving the paper so that it will go to the next line, say form feed and line feed. For that purpose, we know the stepper motors are used in the dot matrix printer. Largely the stepper motors are nowadays used in the robotics. In the industries, nowadays robots are preferred whenever there is a high voltage work or the work related to say high temperature. In that case, for saving humans, the robots are now mostly used. You may have come to know that nowadays robots are also used in the restaurants to serve the food to the customers. Also, they are used in the hospitals to deliver the medicine to the patients. Mainly, that will keep the human interface low as compared to earlier days. So that is the use of the stepper motors. Now, the stepper motors commonly have a permanent magnet rotor surrounded by stator. The construction is shown here. You can see this is the rotor and there are four stator windings A, B, C, D. Here you can see the rotor and the four stator windings. The stator windings are center tapped, or as the four phase or unipolar stepper motor. The permanent magnet rotor, which is surrounded by a stator. Practically, the permanent magnet stepper motor is having 1.8 degree step angle and having total 50 tooth on its rotor. There are 8 main poles on the stator, each having 5 tooth in the pole face. Now here you can see how it rotates step by step to 1.8 degree. Let us say at position 1, then 2, then 3, and then 4. So here the portion shown by yellow, that shows how the motor moves in the steps. Next, to rotate the motor in the steps, you need to output the step sequence. You need to energize the windings, which are called as the bifilar windings. Here you can see the table for that step sequence. You have to output 1001 for 4 windings A, B, C, D, and then go through this step sequence one by one to rotate the motor in the clockwise direction. Here it is shown. If you want to rotate the motor in the anti-clockwise direction, then you have to just reverse this sequence. So the count required will be 9. That means when we consider 8 digits, 99 will be the count required for rotating that in the clockwise direction. However, for rotating in the counterclockwise direction, the initial count has to be 3, means for 8 bits that will be 33. So either 99 or 33, the count has to be loaded initially and then rotate 1 bit at a time. So the motor will move through 1.8 degree step angle each time. To complete one rotation, that means 360 degrees, total steps required will be 360 degree upon the step angle. So you will need the, for let us say in our case for 1.8 degree, total 200 steps will be required for one rotation. Step angle means what? It is defined as the minimum degree of rotation associated with the single step. If the step angle is 2 degree, the number of steps per revolution will be 180. So we can control through the software for how many rotations we want to rotate the motor. Now here it shows the interfacing diagram. We can see the port 1 that is used as output port to output the step sequence, and here you can see using the driver ULN2003, it is interfaced with the stepper motor. This is the bifilar winding having center tap, and the driver is used to isolate the microcontroller from the stepper motor, because to avoid the damage or burnout, this driver has to be used as an isolator in between the motor and the microcontroller. That is how you can connect microcontroller with the stepper motor. Let us discuss about the circuit. The coils ABCD are connected to port 1, that is P1.0, 1.1, 1.2 and 1.3. As the microcontroller does not provide sufficient current to drive the motor, to avoid the loading effect and burnout condition, the motor driver IC that has to be used in between the 8051 and the stepper motor. So here ULN2003 is a stepper motor driver. Mainly the stepper motor is used for position control, then direction control and speed control. You can rotate in clockwise, anti-clockwise direction, with acceleration and with retardation. That means you can control the speed also. For understanding, here the same interfacing is shown, only here the microcontroller chip is shown, and here you can find the port 1 bits from 0 to 3, the current driver. Now here the 4 windings A, B, C, D, and a diode is used as a freewheeling diode in order to dissipate the energy that is generated in this coil. So that is how the stepper motor can be interfaced with the microcontroller. The rest of the circuitry shown here is the on-chip clock oscillator and the reset circuitry for the microcontroller. Next, we'll go through the program. There it shows how the stepper motor that can be rotated. Now in the program, you will find there are 3 fields: label, mnemonics and comment. Here the actual program is there. the program instructions. Begin with the org 000H, that is the start. Org is the directive for the origin, indicates the start of the program. There are different assembler directives like DB, define byte, DW, define word. Those are used for defining the variables. Then EQU for defining the constant. And so these are used as a directions to the assembler, because we use assembler to assemble the assembly language program. We know for assembly language, it is machine dependent as compared to the higher level language, because you need to learn the particular instruction set and then you can write the program using those instructions for that particular processor. But higher level language is machine independent. Let us say C program, which can be executed on any machine, right? So compiler is required there for converting higher level language into the machine language. However, here assemblers are used to convert the assembly language into the machine language, because the microcontroller or microprocessor understands only machine language. So here the first instruction, move a comma hash 99h, that is used to load the initial step sequence into the accumulator. The hash symbol is used to indicate that the immediate addressing mode. As you know, hash for immediate, at symbol for indirect addressing mode. Then if both source and destinations are registered, then register addressing. And if this hash symbol is not used, then it is the direct address. The next instruction, move R0 comma hash 200. Here we are loading the count for how many steps the motor should rotate. Now here we expect one rotation, so we are loading the 200 count because the step angle for our stepper motor is 1.8 degree. Now next instruction, output that step sequence from accumulator to the port 1. Then we're calling a delay routine, absolute call. The delay routine we'll discuss afterwards. So that will insert some delay and then giving the command rotate right. You know, there are two types of instructions, rotate without carry and with carry. So here RRA means rotate right accumulator contents by 1 bit to rotate in state. Then we're using DJNZ R0 comma back, means decrement and jump if not 0 the R0 contents. Here we loaded 200 in the R0, that is nothing but the total count that is required for one rotation. So decrement that count by 1, and if it is not 0, go back. So label that is used, here it is the back. Now these labels are automatically replaced by the actual addresses by the assembler after assembling the file. We write it as a .asm and then we get the .exe file after assembly. Then when the count becomes 0, the motor will complete one rotation and yes jump instruction is used, so it will come out of the loop and yes jump to here. Now here, you know, DJNZ is the conditional jump instruction because certain condition is tested over there. However, yes jump is unconditional jump instruction because no condition is tested, right? Here the call instruction is used. you know there are different calls, absolute call and the long call. That depends on the range. For absolute call, the range is 2K. However, for long call, the range is 64K. Now, the difference between call and jump is that in case of call, there is always a return instruction. Here you can find the return instruction. However, in case of jump, there is no return. So, call where the program will return to the main program. So here you are calling the delay routine. After executing the delay routine, when it finds the RET instruction, return instruction, it will come back and go to the next instruction in the sequence. However, in case of jump, here the address is specified, but here it will remain there only. So that is the difference between call and jump. Now in the delay routine, first load R2 register with FF value, maximum count. Then use the R3 register to load the another FF count. Then DJNZ R3, L1. So till the count becomes 0 of the R3 register, this loop will be executed. Once R3 will become 0, it will go to the next instruction, that is again DJNZ R2. If it is not 0, go to L2. It will again reload R3, then again decrement, jump if not 0 R3, that instruction, that loop will be executed. So this will be repeated till the R2 becomes 0. So that is how the delay that is introduced. We can calculate the exact time also by doing some calculations depending on how many machine cycles required for each instruction. Here in this delay routine, first two instructions requires only one machine cycle. This requires 2 machine cycles, DJNZ instruction, and this also requires 2 machine cycles. The RET requires only 1 machine cycle. So from that, we can calculate the time required for 1 machine cycle is approximately 1.085 microsecond. And then how many times the loop should be executed, L1 and L2. From that, we can calculate the exact delay. And here, that delay routine is called. So, after RET, it will return, and END is again the end of the program. So that is how we can rotate the motor. We can control number of rotations. If I want more, let us say 5 rotations, then here I have to load 5 into 200. So that much count has to be loaded over here. Now here we will not find H because this is in the decimal. This count is in the decimal. Okay. So if I specify H, then this will be invalid because this will be then more than 8 bit, right? However, the register R0 is the 8-bit register. So don't confuse, this is the decimal number. Okay. So that's all how to interface the stepper motor. So in today's session, we discussed about the construction of the stepper motor, application of the stepper motors, and then interfacing. And finally, we discussed about how to write the program to rotate the stepper motor. So, thank you.